In this chapter, we move beyond hydrocarbons and begin introducing functional groups, which are specific arrangements of atoms that give organic molecules predictable chemical and physical properties. And even though carbon and hydrogen still form the backbone of these molecules, adding atoms like oxygen or sulfur dramatically changes how these compounds behave. We will focus on three closely related functional groups: alcohols, phenols, and thiols. We will also introduce ethers briefly, but we go more in depth in a later chapter on those molecules. So before we dive into the details of this chapter, I want to take a moment to frame what you should be able to do by the end of this section. In allied health fields, chemistry is less about memorizing reactions and more about recognizing patterns. Being able to look at a structure or a name and understand how that molecule is likely to behave in a biological or medical context. In this chapter, we'll focus on alcohols, phenols, thiols, and ethers, which show up frequently in medications, disinfectants, metabolic pathways, and biological molecules. You'll practice naming these compounds and drawing them in the common ways you'll see them in textbooks and professional settings. We'll also think about how the structure of these molecules affects properties like boiling point and solubility, which directly relate to how substances move through the body or interact with water. And finally, we'll look at a few key reactions involving these functional groups, not to turn you into organic chemists, remember, but to help you understand how and why these molecules change during processes like metabolism, oxidation, and energy release. And keeping these goals in mind as we move forward and focusing on understanding the why behind the chemistry rather than the memorizing isolated facts is your goal. One important place alcohol-containing compounds shows up in is in anesthesia. Many anesthetic agents are either alcohols themselves or contain alcohol functional groups that play a role in how the drug behaves in the body. The presence of a hydroxyl group can influence how a compound dissolves in the blood, how easily it crosses cell membranes, and how it interacts with receptors in the nervous system. These properties affect how quickly an anesthetic takes place, how long it lasts, and how it's metabolized and eliminated from the body. From an allied health perspective, understanding the basic chemistry behind these molecules helps explain why different anesthetics act differently, even if they are used for similar purposes. As we move through this chapter, keep anesthesia in mind as a real-world example of how small changes in molecular structure, like adding or repositioning an alcohol group, can lead to meaningful differences in biological response. That connection between structure and function is the main takeaway you should focus on. Now that we've seen why these compounds matter medically, let's take a step back and look at the three functional groups we'll be working with in this chapter. At first glance, these molecules may look similar, but small differences in structure lead to important differences in properties and behavior. The first group is alcohols, which are characterized by a hydroxyl group written as an OH, attached to a carbon atom in a carbon chain. This is the most common of the three, and one you've already encountered in earlier examples like ethanol. When you see a hydroxyl on a saturated carbon, you should immediately think alcohol. The second group is phenols. Phenols also contain a hydroxyl group, but the key difference is where the hydroxyl is attached. In phenols, the hydroxyl group is bonded directly to an aromatic ring, such as benzene. That ring structure changes how the molecule behaves, making phenols chemically distinct from regular alcohols, even though they look similar on paper. And the third group is thiols, which are closely related to alcohols but contain sulfur instead of oxygen. In thiols, the functional group is SH, sometimes called a sulfhydryl group. While this might seem like a small substitution, sulfur is a larger atom and less electronegative than oxygen, which leads to very different physical properties and biological roles, especially when we start talking about proteins and enzymes. So as you look at these structures on this slide, don't focus on memorizing each molecule. Instead, practice recognizing the functional group pattern. The OH on the carbon chain, or the OH on an aromatic ring, or the SH attached to the carbon. Being able to quickly identify these features as an alcohol, phenol, or thiol will make everything else in this chapter much easier to follow. So now that you can recognize what an alcohol looks like, the next step is learning how these compounds are named. Naming might feel tedious at first, but the goal here is to simply make sure we're all using the same language when we talk about these molecules in healthcare, science, and professional settings. Again, we're going to be using the IUPAC naming system, which for alcohols is based on the same framework that we used for alkenes, alkanes, and alkynes, with one important change. We start by identifying the longest carbon chain that contains the hydroxyl group, and then we replace the E ending of the alkane name with OL or ol to indicate that the molecule is an alcohol. Using methanol as our first example, the carbon chain contains just one carbon. The parent alkane is methane, and when we replace the E with an OL, the name becomes methanol. Because there's only one possible location for the hydroxyl group, no numbering is needed. For ethanol, the process is very similar. The parent alkane is ethane, which has 2 carbons. Replacing the E with the OL gives us ethanol. Again, there's no need to specify the position of the hydroxyl group because on a 2-carbon chain, it can only be attached in one way, giving us the same molecule regardless of which end the hydroxyl is added to. It's still going to be 1-ethanol or ethanol. Once alcohols get a little larger than methanol and ethanol, naming becomes slightly more involved because the hydroxyl group can be attached to different carbons along the chain, leading to different structures. When that happens, we have to introduce numbering so that the name clearly describes the structure of the molecule. The key idea is that the hydroxyl group has priority when we assign numbers to the carbon chain. We number the chain in the direction that gives the hydroxyl group the lowest possible number. This ensures that anyone reading the name can immediately tell where the functional group is located. For example, in a 3-carbon alcohol, the hydroxyl group could be attached to the end carbon or the middle carbon. And these 2 structures have the same molecular formula, but different properties and different names depending on where the hydroxyl is. Numbering allows us to distinguish between them clearly. In IUPAC naming, the number indicates the position of the hydroxyl group is placed before the parent chain name, followed by the ol ending. As the carbon chains get longer and more complex, the system becomes essential for avoiding confusion and accurately communicating structure. As you work through these examples on the slide, focus on the process rather than memorizing specific names. Find the longest chain, number it so that the hydroxyl gets the lowest number, and then apply the ol ending. That consistent approach will work every time. Up to this point, we've been naming alcohols on straight carbon chains. However, when alcohols form rings, the naming rules stay mostly the same, but there are a couple of simplifications that actually make cyclic alcohols easier. For a cyclic alcohol, the ring itself becomes the parent structure. If there is only one hydroxyl group on the ring, we automatically assign the carbon as carbon 1. Because of that, the number for the hydroxyl group is usually not written in the name. It's assumed. For example, in the structure shown here, the 6-membered ring with a single hydroxyl group is named cyclohexanol. There's no need to specify a number because the hydroxyl group defines the starting point for the numbering. However, if there are additional substituents on the ring, numbering becomes important again. We still assign the carbon with the hydroxyl group as carbon 1, and then we number around the ring in the direction that gives the other substituents the lowest possible number combination. In the second example, the hydroxyl group is carbon 1, and the methyl is on carbon 2, giving the name 2-methyl cyclopentanol. As you look at these structures, notice how the hydroxyl group controls both the parent name and the numbering. It's always taking priority here. The key takeaway is this: for cyclic alcohols, find the ring, locate the hydroxyl group, assign it carbon 1, and then number around the ring only if you need to account for other substituents. Phenols are named a little differently from regular alcohols, even though they also contain a hydroxyl group. The key difference is that the phenols, the hydroxyl group, is attached directly to the aromatic ring, usually a benzene. Because of that, the base name for these compounds is phenol, which includes the hydroxyl in the name, rather than using the OL ending of benzene, such as like benzenol. When there are no other substituents on the ring, the compound is simply called phenol. The hydroxyl group automatically defines carbon 1, so no numbering is needed in that case either. When additional substituents are present on the aromatic ring, we do need to introduce numbering. The carbon bonded to the hydroxyl group is always assigned as carbon 1, and the ring is numbered in either direction that gives the other substituents the lowest possible numbers. You'll notice that phenols are often named in two ways. One option is the IUPAC system, which uses numbers to indicate the substituent position, such as 3-chlorophenol or 4-ethylphenol. The other option is the common naming system, which uses ortho, meta, and para to describe where the substituent is located relative to the hydroxyl group. For example, a substituent next to the hydroxyl group is ortho. 1 carbon away is meta, and directly opposite on the ring is para. In allied health settings, you'll often encounter both naming systems. So the goal here is recognition, being able to look at the structure and understand that what the name is telling you about the substituent placement. As you look at these examples, focus on 2 steps. Identify phenol as the parent structure, and then determine where any additional groups are located relative to the hydroxyl group. If you can do that, phenol naming becomes pretty straightforward. Let's practice naming this compound. First, identify your parent chain or longest chain by counting the longest continuous chain of carbons. Here we have 2 options, but both at 6 carbons long, and honestly, with this example, either way we count, we're going to end up with the same parent chain of hexane. Next, identify the functional groups that we have present. Here we have a methyl, 1 carbon long acyl chain, and a hydroxyl group. In this case, the hydroxyl group will take numbering priority, so we can number the chain starting at the end closest to the hydroxyl, making its carbon number 2, and the methyl coming off of carbon 5. Finally, we put the parent chain suffix to match the higher priority functional group and put it all together, giving us 5-methyl-2-hexanol. Now, you may be asking, how do I know which group gets priority, the methyl or the alcohol? In general, more oxidized functional groups take priority over less oxidized one. So groups like carboxylic acids, aldehydes, ketones, and esters outrank alcohols and thiols, which in turn outrank alkanes. But I do not expect you to memorize that. You will be given a table for your exam that lists the functional groups ranked by priority. The key is to know how to use it. So look at last year's exam now to see an example of that table and learn how to read it before the exam. Okay, so now it's your turn. Let's open the in-class assignment for Chapter 13 and complete questions 1A and B to practice naming an alcohol and a phenol. So pause the lecture here and come back when you're done. Up to this point, we've been focusing on how alcohols are named. Now we're going to look at how alcohols are classified, which is a separate idea, but an important one because classification helps predict chemical behavior, especially in reactions and metabolisms. So alcohols are classified as primary, secondary, or tertiary based on the structure of the carbon atom attached to the hydroxyl. This is the key point. We are not classifying the entire molecule. We are classifying that specific carbon. A primary alcohol is one where the carbon bonded to the hydroxyl group is attached to only one other carbon. The remaining bonds on that carbon are then to hydrogens. Primary alcohols are often found at the end of a carbon chain. A secondary alcohol has the hydroxyl group attached to a carbon that is bonded to 2 other carbons and 1 hydrogen. This typically places the hydroxyl somewhere in the middle of a carbon chain. And finally, a tertiary alcohol has the hydroxyl group attached to a carbon that is bonded to 3 other carbons and no hydrogens. This creates a more crowded structure around the hydroxyl group, which will then affect how the alcohol reacts. So when you're classifying alcohols, don't count the oxygen or hydrogen in the hydroxyl group. Only count how many carbon atoms are attached to the carbon holding the hydroxyl. If you do that consistently, classifications become very straightforward. This classification will matter later on when we start talking about reactions like oxidation and dehydration, because primary, secondary, and tertiary alcohols behave very differently under these conditions. So turning back to mastering chemistry, let's practice identifying the different classifications of alcohols by answering question 2. Remember, the key is to look at how many carbon-carbon bonds are on the carbon that has the hydroxyl functional group attached to it. So pause here and return when you're ready. Methanol is a simple alcohol that is commonly found in industrial solvents, antifreeze, and paint removers. Because it looks and smells similar to ethanol, it is especially dangerous if accidentally ingested. The reason methanol is so toxic is not just because of the compound itself, but what the body turns it into. When methanol enters the body, it is metabolized by enzymes in the liver and oxidized to form formaldehyde and then further to formic acid. These products are far more harmful than methanol alone. Formaldehyde and formic acid interfere with normal cellular function, particularly in the nervous system and optic nerve. And this is why methanol poisoning can cause symptoms such as headache, nausea, blurred vision, blindness, and in severe cases, death. From a chemistry perspective, this is a powerful example of why alcohol classification and oxidation reactions matter. Small differences in molecular structure can lead to very different metabolic pathways and health outcomes. From a healthcare perspective, recognizing sorry about that. So from a healthcare perspective, recognizing the sources and risks of methanol exposure is critical for prevention and treatment. The key takeaway is that understanding the chemistry of alcohols helps explain not only how these substances react in the lab, but also how they behave in the human body. Phenols are commonly found in plants, especially in the essential oils that give herbs and spices their characteristic aromas and flavors. On this slide, you can see examples of phenolic compounds found in familiar plants like cloves, thyme, nutmeg, and vanilla. Compounds such as eugenol, thymol, and vanillin all share a common feature, a hydroxyl group attached directly to an aromatic ring. That phenol structure contributes to both their biological activity and their sensory properties like smell and taste. From a chemistry perspective, the phenol group makes these molecules more reactive than typical alcohols and gives them mild antimicrobial and antioxidant properties. This helps explain why plants use these compounds as part of their natural defense systems against microbes and pests. From a health perspective, it's important to separate chemical properties from medical claims. While these compounds are used in foods, fragrances, and some topical products, natural does not automatically mean safe or therapeutic. Concentration, route of exposure, and context all matter. And the key takeaway here is that phenols are widespread in nature and play real biological roles. Understanding their structure helps explain why they interact with living systems in the ways they do, sometimes beneficially, sometimes harmfully. So far, we've talked about alcohols and phenols, which both contain oxygen. Now we're going to take a look at a closely related functional group called thiols. Thiols are very similar to alcohols in structure, but instead of a hydroxyl group, they contain an SH or sulfhydryl group. Even though this looks like a small change, replacing oxygen with sulfur, it has a big impact on how these molecules behave. Sulfur is larger and less electronegative than oxygen, which makes thiols less capable of hydrogen bonding and gives them very different physical and chemical properties. One reason thiols are easy to remember is their distinctive odors. Many thiols have extremely strong smells, even at very low concentrations. A classic example is the compound responsible for the smell of skunk spray, shown here. That odor is due to the thiol structure, not because the molecule is large and complex, but because sulfur-containing compounds interact strongly with our smell receptors. Beyond smell, thiols are biologically important. The sulfhydryl group found in proteins play key roles in enzyme function and protein structure, something we'll touch on briefly as we go forward. And as we move into thiols, focus on recognizing the SH functional group and understand how swapping oxygen for sulfur changes molecular behavior. Just like with alcohols and phenols, structure drives function. To name a thiol using the IUPAC system, we start the same as everything else. We're going to identify the longest carbon chain that contains the sulfhydryl group. The parent name is based on the corresponding alkane, but we replace the E ending with a thiol. If the carbon chain is long enough that the sulfhydryl group could appear in more than one location, we then introduce numbering. The chain is numbered so that the carbon bonded to the sulfur gets the lowest possible number, just like we did for alcohols. For example, a 3-carbon chain with the sulfhydryl group on the first carbon is named 1-propanethanol. Propanthenol. I have a hard time pronouncing this. 1-propanethiol. If the sulfhydryl group is attached to a different position, that number must be included in the name. You may also encounter thiols in molecules that contain double bonds. In those cases, the position of the double bond is indicated using the same rules you learned for alkenes, and the thiol suffix is still used to show the presence of the sulfhydryl group. The most important takeaway is that the thiol naming mirrors alcohol naming very closely. If you can recognize alcohols, you already have the tools to name thiols. You just need to recognize the sulfhydryl group and swap the ol for thiol. The last functional group we're going to introduce in this chapter is ethers. Ethers are closely related to alcohols, but instead of a hydroxyl group, they contain an oxygen atom bonded between 2 carbon atoms, written as COC. One helpful way to think about ethers is that they look a lot like an alcohol, where the hydrogen on the oxygen has been replaced by another carbon group. That single structural change removes hydrogen bonding between ether molecules, which gives ethers different physical properties compared to alcohols. On this slide, you can see a few common examples. When the oxygen connects 2 identical carbon groups, like 2 methyl groups, the compound is named methoxymethane, also known by the common name as dimethyl ether. When the groups are different, such as an ethyl group on one side of the oxygen and a methyl group on the other side of the oxygen, we use a systemic approach to naming. In IUPAC naming, ethers are treated as alkoxy substituents attached to a parent chain. The smaller carbon group is named as the alkoxy group, like methoxy or ethoxy, and the larger group becomes the parent chain. So that's why CH3CH2OCH3 is named, sorry about that, that's why CH3CH2OCH3 right here is named methoxyethane, because the longer chain is going to get the alkane name and the shorter chain gets the oxy substituent naming, methoxy. Ethers can also be attached to aromatic rings. When an ether is bonded to a benzene ring, the alkoxy group is treated as a substituent on benzene, giving names like methoxybenzene, which you can also see is commonly called anisole, or its common name. So why don't we practice naming this molecule? So the first thing you want to do is identify and write the name of the longest alkane chain. So looking on either side of the oxygen, we have 2 carbon long chain ethane, or 1, 2, 3, 4 carbon long chain butane. So since butane is our longest, that's going to be our parent chain. Then we're going to identify and write the name of the shorter alkane chain proceeding from the parent chain. Again, butane is our longest parent chain, so ethane is going to become our second chain, and we're going to write that in front or preceding the parent chain. Then we change the suffix of the shorter chain to oxy and identify the location based on the parent chain. So it would be 1-ethoxybutane, since it is coming off this carbon on butane. So we're going to identify this carbon as carbon 1. So 1-ethoxybutane. Why don't you practice this yourself? Let's practice naming and identifying ethers by answering questions 3A, B, and E. I went ahead and gave you credit for parts C and D, but you can always come back to those later for practice. When you're done, come back to the video. Ethers also have an important role in medicine, particularly in history and practice of anesthesia. Several anesthetic agents are ethers or contain ether linkages, because this functional group gives molecules properties that are especially useful in the clinical setting. One key feature of ethers is that they are relatively nonpolar compared to alcohols and do not form strong hydrogen bonds with each other. This makes many ethers volatile, meaning they can easily vaporize, which is essential for inhaled anesthetics. On this slide, you can see an example of a modern inhalation anesthetic, isoflurane, also known by the trade name Forin. Structurally, it contains an ether linkage along with halogen atoms like fluorine and chlorine, as you can see right here. So there's our ether, and then there's our halogen of chlorine and fluorine as well on lots of different carbons. Structurally, these features help control how the compound is absorbed into the bloodstream, how quickly it reaches the brain, and how it's eliminated through the lungs. From a chemistry perspective, the ether functional group contributes to the molecule's ability to cross cell membranes, including the blood-brain barrier. From a healthcare perspective, this translates into rapid onset and controlled depth of anesthesia when administered properly. So to understand why alcohols and ethers have different boiling points, we need to focus on intermolecular forces, specifically hydrogen bonding. So alcohols contain a hydroxyl group, right? You have both the oxygen and the hydrogen, which then allows them to donate and accept hydrogen bonds with each other. The hydrogen attached to the oxygen is partially positive, and the oxygen has a lone pair of electrons, so neighboring alcohol molecules can form strong attractions with each other. These hydrogen bonds create a network that holds the molecules together more tightly. Because more energy is required to separate molecules that are hydrogen bonded, alcohols generally have higher boiling points, going from the liquid to the gas phase, than other organic molecules of similar mass. Ethers, on the other hand, behave differently, even though they also contain oxygen. In an ether, the oxygen atom is bonded to two different carbon atoms, right? So there's no hydrogen coming off of that oxygen like we see with the alcohol. Because of that, that means they cannot donate hydrogen bonds, although they can accept them. Because ether molecules cannot hydrogen bond with each other, the intermolecular forces between them are weaker than what we see in alcohols. As a result, ethers will have lower boiling points than alcohols with similar molecular weights. This difference helps explain why ethers are often more volatile, which is one reason they've been useful in medical applications such as anesthesia. It also affects how long substances remain in the body and how easily they evaporate. So the key takeaway here is even small structural differences, sorry, I don't know why my slides keep doing that. Even small structural differences like the presence or absence of a hydroxyl hydrogen can lead to significant differences in physical properties and their medical purposes. Hydrogen bonding plays a major role in determining boiling point, and alcohols and ethers are clear examples of that principle. Now let's use the same idea of hydrogen bonding to understand the solubility of alcohols and ethers in water. So water is able to form hydrogen bonds very easily. So whether a substance is soluble in water depends largely on whether it can also participate in hydrogen bonds. As you remember, alcohols contain the hydroxyl group, right? Oxygen and hydrogen, which allows them to both donate right here and accept hydrogen bonds with water molecules. Because of this, small alcohols like methanol and ethanol are highly soluble or even completely miscible in water. As the carbon chain of the alcohol gets longer, however, the non-polar carbon-hydrogen portion begins to dominate. So even though the hydroxyl group can still hydrogen bond, the overall molecule becomes less compatible with water. And so this is why larger alcohols become less soluble as their carbon chain increases in length. I must have some sort of timing automation going in these slides, and I'm sorry. All right, ethers interact with water a little differently. So if you remember, the oxygen is between two carbons, so there's no hydrogen coming off that oxygen. What that means is ethers can accept hydrogen bonds from water, but they cannot donate hydrogen bonds from water, right? Because they don't have that hydrogen to donate. So as a result, ethers are generally less soluble in water than alcohols of similar size. So the overall pattern to remember is this: hydrogen bonding increases solubility in water, but molecular size still matters. Alcohols tend to be more soluble than ethers, and increasing carbon chain length reduces the solubility for both. This same reasoning applies throughout organic chemistry and biochemistry, especially when we begin to think about how molecules move through the body or dissolve in biological fluids. Phenols behave a little differently from regular alcohols when it comes to solubility, and that difference comes from both their structure and their chemistry. So like alcohols, phenols contain the hydroxyl group that can form hydrogen bonds with each other in water. This gives phenols some degree of water solubility, especially when the aromatic ring is small or has other polar substituents attached to it. However, the aromatic ring itself is largely nonpolar, which limits how soluble phenols can be compared to small alcohols like methanol or ethanol. As the ring gains additional nonpolar groups, the solubility in water generally decreases. What makes phenols especially interesting is that unlike typical alcohols, phenols can act as weak acids. The hydrogen on the hydroxyl group can dissociate, forming a phenoxide ion, as you see here. This happens more readily in phenols than in alcohols because the negative charge left behind on the oxygen can be stabilized by resonance across the aromatic ring. When phenols lose a proton and form an ion, their solubility in water increases because charged species interact more strongly with water molecules. So this is why phenols are often more soluble under basic conditions than under neutral conditions. So on this slide, we're pulling together everything we've talked about so far to reinforce the relationship between molecular structure, chain length, and physical properties, specifically boiling point and solubility, as you can see here in these two columns. As the carbon chain length increases, both alcohols and ethers experience stronger dispersion forces because the molecules are larger and have more surface area. This causes boiling points to increase as chain length increases, regardless of the functional group. However, when we compare alcohols and ethers of similar size, alcohols consistently have higher boiling points, and that's because the difference comes from hydrogen bonding. Alcohols can hydrogen bond with each other, while ethers cannot. So alcohol molecules require more energy to separate. Solubility shows the opposite trend. Small alcohols and ethers are more soluble in water, but as the carbon chain grows, the nonpolar hydrocarbon portion begins to dominate, and this reduces compatibility with water because This reduces our compatibility with water, causing solubility to decrease as chain length increases. Alcohols remain more soluble than ethers at comparable sizes because they can both donate and accept hydrogen bonds with water. Ethers can only accept hydrogen bonds, which limits their interactions with water molecules. So the big picture takeaway is this: increasing chain length raises boiling point but lowers water solubility, and hydrogen bonding explains why alcohols behave differently from ethers. If you can recognize these two factors, functional group and chain length, you can reliably predict physical properties without having to memorize this data. So to practice these concepts, let's work questions 4 and 5 in Mastering Chemistry. Feel free to refer back to the previous slides as you work through these questions. When finished, come back to the lecture and we'll talk about the different reactions of alcohols and thiols. In this next part of the lecture, we will be discussing the various reactions that alcohols and thiols can undergo and how to predict their products. Starting with one of the most common reactions of alcohols, dehydration. The word dehydration literally means the removal of water. In a dehydration reaction, an alcohol loses a molecule of water through the loss of the hydroxyl and a neighboring carbon's hydrogen, converting the alcohol to an alkene. This reaction typically requires heat and an acid catalyst, which you'll often see written as H+ and heat above the reaction arrow. On the slide, you can see the key pattern to recognize. The hydroxyl group from the alcohol and a hydrogen atom from a neighboring carbon are removed together to form the water molecule. And what remains is a carbon-carbon double bond. That's why the product of a dehydration reaction is always an alkene, as you can see here. Again, you don't need to memorize mechanisms for this course. Instead, focus on recognizing the before and after. Alcohol in, alkene plus water out. If you can identify where the hydroxyl group is and where a hydrogen atom can be removed, you can predict the products of a dehydration reaction. So when we have a primary alcohol, or the hydroxyl group is at the end of the carbon chain, then there's only one possible product. The alkene will happen between carbons 1 and carbon 2. However, when we have a secondary or tertiary alcohol, or the hydroxyl group is in the middle of a chain, there are a few possibilities of where the double bond can go. Often what we see is that the double bond occurs between two carbons with less hydrogens on them, making the less substituted alkene a minor product, as you can see here, right? So if our hydroxyl is on a middle carbon, it is more likely that the double bond is going to go in this direction than it is this direction, because this terminal carbon right here has 1, 2, 3 hydrogens on it, instead of this carbon that just has 2 hydrogens on it. So that's what we mean by the less substituted would be where the double bond goes in this direction, versus the more substituted where the double bond goes in the backwards, or more toward the middle of the chain. In addition to substitution, the geometry of the alkene also matters. So when both cis and trans forms are possible, the trans alkene is going to be favored. In the trans arrangement, the larger groups are positioned opposite of the double bond, which is going to reduce crowding and make the molecule more stable. Putting these ideas together, dehydration reactions tend to favor the alkene that is both more substituted and trans. That product is going to be lower in energy, so it forms more readily and in greater amount. So let's practice predicting the major product of dehydrating both a primary and a secondary alcohol with question 6. Again, refer back to the previous slide when predicting the product for 6b. Pause, and when you're ready, come back. Now we're going to introduce another important class of reactions involving alcohols, oxidation and reduction. These reactions are especially relevant because they mirror processes that happen in the body, particularly during metabolism. In organic chemistry, oxidation and reduction are best understood by focusing on bonds to oxygen rather than memorizing electron transfer rules. A simple way to think about it is this. Oxidation means increasing the number of bonds from carbon to oxygen, or decreasing the number of bonds to hydrogen. Reduction is the opposite, decreasing bonds from carbon to oxygen, or increasing the number of bonds to hydrogen. A primary alcohol starts with one bond between carbon and oxygen. When it is oxidized, it forms an aldehyde, which has 2 bonds to oxygen. With further oxidation, it can become a carboxylic acid, which has 3 bonds to oxygen. A secondary alcohol also begins with 1 bond to oxygen. When oxidized, it forms a ketone, which has 2 bonds to oxygen. Unlike primary alcohols, though, the secondary alcohols do not oxidate further under normal conditions because the ketone carbon has no more hydrogens to lose. So notice, no more hydrogens. Tertiary alcohols generally do not undergo oxidation. There's no hydrogen on the carbon attached to the hydroxyl group to remove. So if you notice, this carbon has 1, 2, 3 carbon bonds and 1 oxygen bond. There's no hydrogens here. Thiols can also undergo oxidation, but the outcome is different from what we saw with alcohols. Instead of forming carbon-oxygen double bonds, the oxidation of thiols leads to the formation of a disulfide bond. When 2 thiol groups are oxidized, the hydrogen atoms are removed and the 2 sulfur atoms bond to each other, forming a disulfide, written as -S-S, right? As you can see, let me get my laser, as you can see right here. This reaction is shown schematically on the slide as oxidation, often referred to as an O. This type of reaction is extremely important in biology, especially in proteins. A key example is the amino acid cysteine, which contains a thiol group. When 2 cysteine residues in a protein form a disulfide bond, they create a cross-link that helps stabilize the protein's shape. In hair, these disulfide bonds play a major role in determining whether hair is straight, wavy, or curly. Curly hair contains more disulfide cross-links between protein strands, which locks the hair into the curved shape. Fewer disulfide bonds allow the hair to remain straighter. This also explains how chemical hair treatments work. Processes like perms and relaxers temporarily break and reform disulfide bonds, allowing the shape of the hair to be changed. The key takeaway here is that oxidation of thiols creates disulfide bonds, and those bonds have real structural consequences in biological systems. This is another strong example of how simple chemical reactions can have a visible, everyday effect. This slide shows how ethanol is oxidized in the body, and it's a great real-world example of the oxidation reactions we just learned. Ethanol, which is a primary alcohol, is first oxidized to ethanal, also called acetaldehyde. You can see that this step increases the number of bonds between the carbon and oxygen. This is exactly how we define oxidation in organic chemistry. Acetaldehyde is a highly toxic intermediate. Many of the negative effects associated with alcohol consumption, such as headache, nausea, flushing, and hangover symptoms, are linked more to acetaldehyde than to ethanol itself. In the body, acetaldehyde is quickly oxidized further into the products that can eventually be broken down into carbon dioxide and water, allowing the carbon atoms to be eliminated through normal metabolic processes like respiration. The key chemistry takeaway is that ethanol behaves just like... Oh, this timing thing's really annoying. I'm so sorry. The key chemistry takeaway is that ethanol behaves just like the primary alcohols we discussed earlier. It oxidizes first into an aldehyde and then continues down an oxidation pathway, eventually to CO2 and water. The health takeaway is that the body is constantly working to detoxify alcohol by converting it into substances that can be removed. This is a strong example of how understanding organic reaction patterns helps explain real physiological processes, including why alcohol affects the body the way it does. So let's see if you can correctly predict the products of oxidation to alcohols. Let's work 7A and B and C. Again, if you get stuck trying to draw these in Mastering Chemistry, try drawing them on paper first and reach out if you have any questions. When you're ready, come back and we're going to summarize the chapter. We're going to end this chapter with a concept map that pulls together all of the major ideas you've seen about alcohols, phenols, thiols, and ethers. The goal here isn't memorization, it's recognizing relationships and patterns. On the right side of the map are compounds with carbon-oxygen single bonds, alcohols, phenols, and ethers. These functional groups differ in structure, but they share common themes in naming, physical properties, and reactions. Alcohols in particular are very reactive. They undergo dehydration to form alkenes, or oxidation, where primary alcohols become aldehydes and then carboxylic acids, and secondary alcohols become ketones. Ethers behave differently. They're relatively unreactive, but they do undergo combustion, producing carbon dioxide, water, and energy, something we connect directly to anesthesia and metabolism. On the left side of the map are compounds with carbon-sulfur single bonds, the thiols. And instead of forming carbon-oxygen double bonds when oxidized, thiols undergo oxidation to form disulfides. And this reaction is biologically important, especially in proteins like keratin, where disulfide bonds affect structure and strength. What this concept map highlights is the functional group identity controls behavior. Once you can identify the functional group, you can predict naming, physical properties like boiling point and solubility, and the types of reactions that will occur. This chapter sets up ideas you'll continue to use moving forward, especially oxidation, structure-property relationships, and how organic chemistry explains real biological and medical processes. So I'll see you guys next time. Thank you.